Okay, so here we're going to talk about vector algebra. Vectors are really important in the field of physics. I'm assuming you know the basic idea of what a vector is, and maybe you've talked about it in trig or whatever. This will cover probably, hopefully, some refreshment stuff, but maybe something new. So let's start with the vector A, which is equal to just I plus 2j plus 3k. And real quick, this is the same thing as just having one I. But you might see it written like that. And let's also have a vector B, which is equal to 4i plus 5j plus 6k. First thing we're going to talk about is finding the magnitude of a vector. So these vectors have three components. They have an I hat, j hat, and k hat, or an x, y, z component to it. And if you want the magnitude, it's really nice. So let's look at a two-dimensional case where you have this x component and then this y component. If you wanted to find this length r, if we had x and we had y, right? R is just the square root of x squared plus y squared. Right, there's your magnitude. And this translates very nicely to the three-dimensional case. So, for example, the magnitude of A is just the square root of 1 squared plus 2 squared plus 3 squared, all square root, which is, let's see, this is 9, this is 4, this is just 1, so square root of 14. Keeps catching me there. Square root 14. Let's try B, which was 4, 5, and 6. Right, same thing. 5 squared, 4 squared. We'll start with the 4 plus 5 squared plus 6 squared. Let's see, that's 16 plus 25 plus 36. Let's see. If we added 20 to that, that gets us 56 plus 5 is 41. Let's see. 77? 77, 36 plus 25. Right, that's 50, so that puts us at 61. Plus the 10 is 71 plus 6, 77. Yeah. So that's the magnitude of our two vectors. That's kind of like this R. Okay. And that's what these bars denote, is that we're looking for the magnitude. The next thing we need to talk about is the dot product. And the way I think of the dot product is basically telling you, the dot product and the cross product are telling you really how parallel and perpendicular two vectors are. So let's look at A dotted with B. That can be thought of as just taking the components. So in this case, we would do AX times BX plus BY, BZ plus, that should be AY, BY plus AZ, BZ. Now the dot product spits out a scalar, as you can see, which is different from the cross product. Another way to think about the dot product is the magnitude of A, magnitude of B, times cosine of theta, where theta is the angle between vectors A and vectors B. So let's go ahead and let's find the dot product using this way first. Let's see. We have 1 times 4, right? Because of our 1 times 4. And then we'll do plus 2 times 5. And then plus 3 times 6. And we'll get this scalar in return. So we have 1 times 4 plus 2 times 5. You see why I picked these numbers now. Plus 3 times 6. This is 4 plus 10 plus 18, which is, let's see, 14. So plus 10 to that makes it 28. So 32. So there's our dot product. The cross product is another way of multiplying vectors. But this one will spit out a, so this is a scalar, it's just a number. This spits out another vector, so that's one of the two differences. That can be thought of as the magnitude of A times magnitude of B times sine of the angle between those two vectors. Or, if you want to do it the long way, it's the determinant, where this first row is our unit vectors. And we're doing A, so we, in this middle row of our determinant, we'll do 1, 2, 3. Cross B, 4, 5, 6. And we can compute this determinant. And the way that we do this, I'll just have to unhighlight it, just so you can see what I'm trying to talk about here. So the first thing we do is we block this out, and we block this out. And now we have a 2 by 2 determinant of just this stuff. Now we can do Kramer's rule. So the way we do this is 2 times 6. Let's see. 2 times 6 is 12. Minus 3 times 5 is 15. And we pivoted off this I. So that's your I hat. Kramer's rule is if you have A, B, C, D determinant, that's equal to AD minus BC. Okay. So let's see if I can get rid of just the highlighted part. Did pretty good there. Now we want the J component. So, oops. So we first cross out this J area. And we still go across. And now we have another 2 by 2 determinant with 1, 3, 4, and 6. So this 1 is our A. And real quick, for the J component, we put our negative here. So A times D is 1 times 6, that's 6. Minus 3 times 4, that's your BC, that's 12. And that's our J component. And we go back to our plus. And for our K, we again block this out. I physically, like the yellow part that I've been highlighting, I'll physically close that off, cover it with my hand, so I am just looking at that. Okay, and then we have, let's see, 5 minus 8K. So that nicely simplifies to minus 3I plus 6J minus 3K. And as I said earlier, the cross product spits out another vector. And real quick, actually, because if you look at this, this is a magnitude times a magnitude sine of theta. Actually, there's an in vector there. You don't need that when you're computing it, obviously, but it's still technically there. Okay, so we got this other vector. We showed you the determinant way of doing it. We talked about the dot product. So that's pretty good, I would say. Now that we have that, let's consider this. Let's find cosine of theta using the definition of our dot product. So we know A times B from the above is equal to the magnitude of A times the magnitude of B, cosine of theta. So if we want to know theta, it's just the dot product. I'm going to stop drawing arrows because I'm lazy. Times the magnitude of A, magnitude of B, is cosine theta. And we calculated the dot product earlier, which was 32 over our magnitudes, which were 14 and 77. So root 14 times root 77, let's see, that is square root of 1078. Maybe that can be cleaned up, but that's good enough for now. So that's what our cosine of theta is equal to. You can use this dot product. I should probably box this for you guys because this is like your main equation here. Which I guess all of this really is. I should box this whole thing. I covered the arrows, it's fine. That's ugly. Okay, that's fine. There's your dot product. I guess if you wanted to be general here, this would be I, J, K, A sub X, A sub B. Should turn the shape off. A sub Y, A, Z, and then the same thing with our other vector, if we wanted to be as general as possible. Right. Okay, so now that we have that, so let's say you have vector A dotted with vector C. I know I'm not drawing the arrows because I'm lazy. And you know that that's equal to 10. And you know the angle between those two vectors is just 30 degrees. Can you find vector C? Or at least the magnitude of it? Yes, because we know A dot C is the magnitude of A, magnitude of C, cosine of theta. And this is 10 divided by the magnitude of A. What's the magnitude of A was root 14 times cosine of 30 degrees is equal to our magnitude of C. And cosine of 30, the way I remember it is, so cosine of 30 is kind of closer to our, if we think on our unit circle, it's more over here than up here. So over here, your x is bigger than your y, so cosine must be root 3 over 2. It's in the denominator, so that's actually going to be 2 times 10, so 20, over root 14 times 3, so that's root 42. That's the magnitude of C. So there we go. So that's kind of how we can use, it's a rough box, but just roll with it. That's how we can use the dot product to manipulate equations and find out information about vectors that might be helpful in solving some of our problems. Just so you know, oops, that's for the differential equation section. Just so you know, this isn't completely useless. We often we calculate work during a dot product. When you do electricity and magnetism, there's a lot of dot products. When you look at torque, cross product. So these basic vector operations are very important. It's important we understand what they are. Another thing I should mention about the cross product is the vector that it spits out. Let's say this spits out vector, we used C earlier, so D. D is going to be perpendicular to both A and vector b. And what I mean by that is, I'll talk about it over here. So let's say vector A cross vector B equals vector D. Okay. So let's say we have vector A. Let's say we have vector B. And we have the angle theta. So vector D is going to be perpendicular to both A and B. Well, the only way it can be perpendicular to both would be if it comes either out of the page or into the page. So this indicates a vector going out of the page, like if you saw the tip of an arrow. And this goes into, like, looking at the back of an arrow. So D is either going into or out of the page. There's no other way about it. And the way that we determine the sign of vector D, if it's going into or out of the page, is you take your right hand and you place your fingers along your A vector. And then you want to curl your fingers. You want to curl them in the direction of A. So if you did that and you curled them, you see that your thumb would be pointing out. So that would indicate that this is the direction of D. It's going out of the page. So that's kind of cool. We see the A cross B points in the positive Z direction. Let's flip it around, though. Let's say we wanted to do B cross A. Well, if you put your right-handed fingers onto vector B now, because that's the first vector we see, the only way you can comfortably curl your fingers towards A is with your thumb down. So that gives us negative dz. So what does that mean? Well, there's a property of vectors, and I didn't show you guys every property. There's a lot of properties of vectors, and we can talk about that. But it's actually the opposite of, B cross A. You'll get the opposite vector. So order matters with our cross product, because if you get your order backwards, then you'll have your vector going in the opposite direction, which isn't good. So hopefully that was at least mostly a review. If not, if you're in a lower level math, that's okay. This is good. This is some basic vector algebra that I think will be helpful. Good news. Next video is touching on calculus. So that's a little bit more fun. And then after calculus, differential equations. So things are going to jump up a little bit in some of the math you need to know, but that's okay. So yeah, awesome. Hopefully I'll do another video tomorrow.